Hello everyone and welcome back to sort of a new series. So as some of you might know that have been watching the channel, I've kind of covered a handful of different topics, but I kind of wanted to give like a intros, beginner's guide to some linear algebra concepts. I don't know if you're watching, shout out to you. Good luck with the series. Feel free to reach out to me if you have any questions. Anyways, let's get into it. So we're going to be talking about an intro to both matrices and vectors today. So vector can be defined in a multitude of different ways. There's a lot of ways to kind of approach them. But for now, I'm going to give kind of a simple definition. I'm actually going to define them as a matrix, which I've defined down here. And you can think of them as an n by 1 matrix, where n is anything, but 1 is referring to this like width, as we're going to see shortly. So the 1 is just going to be this width, right? You can see this width is always 1, but this length over here can be anything, right? So here this is a 2 by 1 matrix. Excuse me, sorry. This is a 3 by 1 matrix, and this could be any length, right? I have the dot, dot, dot. So this could be pretty long. And to keep things kind of simple for now, we're really considering the versions where these are just like numbers. You could have functions as entries, you could have all sorts of different things, but right now we're keeping things simple. We're just going to have numbers as our entries. So that's essentially the idea of a vector. Now, a matrix in its most like general, like broad definition is just a rectangular array of, like in this case, just numbers, right? And I've kind of detailed the sizes below. So when we say 2 by 2, the way we're measuring is we go down. So this is 2, and then this is also 2. So I know square matrices are not always the best because they kind of, like, it's hard to tell which is which. So I've included some non-square ones. So 3 by 2 is we have 3 going this way, and then we have 2 going this way. Or with the 1 by 3, we have 1 going this way, and then 3 going that way. It's a 1 by 3 matrix. So take a second to look at these. I've intentionally not made these problems too hard. Just try and find the size. Pause the video, write down your predictions, and then I'm just going to go over them quickly. Okay? So this first one is going to be 3 by 4, right? That's because we're going 3 this way and then 4 this way. So I'm going to say that is 3 by 4. The second one is going to be 2 by 1, and then this last one is 2 by 3. If this didn't make sense to you, look at this again, maybe try it again on your own, because this is very important for some of the stuff we'll cover later in this video. Again, this is all supposed to be like new information, so no worries if it doesn't make sense right away. Okay, so let's take a look at some properties of these vectors and matrices, okay? So I know there's a lot of writing on here, but I promise you I'll try and get to everything. So here I've just kind of like labeled some things up ahead, just some general matrices and vectors. So first is the property of scalar multiplication. And that says, right, if we have some vector v defined as above, if we multiply t, it'll just multiply each one of the entries. And I'm going to use this word a lot. Entries are just what we call like the components of vectors. So this is an entry of a vector, this is an entry of a matrix. Sometimes you can index the entries of a vector. So I can say perhaps that a1 of 1 is equal to a. And what I'm doing, right, I'm just saying, let's go down to the first row and the first column, and that's the entry there. So that's maybe not something super relevant, might not need that just yet, just something to know perhaps. So anyways, that property of scalar multiplication is pretty nice, and the same thing works for matrices. So maybe something to keep in mind generally is that vectors are, I guess, just like a version of matrices. So that's why this kind of works for both of them. So TA is just the same thing as you multiply each one of the entries by t. And that works out pretty nicely. And then the next we have the idea of addition. And this addition, very important note, right? I'll circle that over here. It's only going to happen if they're the same size, right? So let's just say on the example, I'm going to put an example over here. Let's say I'm adding AB plus, let's say CDE. We actually say that this addition is going to be undefined. So that doesn't really have any meaning because you're adding two things with different size. So please don't do that. So over here, right, we've just said that v plus w, we can just add it component-wise. So it's x plus z on the top, and then we have y plus w on the bottom. And the same thing with matrices, you add, because these are both 2 by 2 matrices, so we can just say a plus e, b plus f. so on and so forth. So those are two really important properties. In fact, they might seem very simple, but these two properties, scalar multiplication and addition, are two of like the most important properties that come up in linear algebra time and like again and again. So they're important to know why they work. Okay, so I know you guys love your examples. Let's take a look at some examples. These are always helpful to get us going in the right direction. So I've labeled everything here and I've said compute the following if possible. Okay, so as always, take a second, try these on your own, and then you can play the video and see my explanation. Okay, let's jump right into it. So the first one, we're going to be multiplying the vector x by 2 and then subtracting y. So let's first do multiplying by 2. So we have 2 times -2, -4, and then 2 times 3 is 6. And then we're going to subtract y, which in this case is just going to be 0, 1. And when we compute that, our answer is going to come out to -4, 5. Nice. Okay, so next we're going to be doing y minus 2/3 of z. Now I did kind of write this in a tricky way on purpose, where 2/3, maybe you're thinking, oh, we can kind of just maybe take the first two elements. Nope, these are different sizes, so this is going to be undefined. Don't do that. And then the last one I think is a pretty easy one. We're just doing a plus b. In this case, they're both 2 by 2 matrices, so that's completely defined. And so we're going to have the first two elements, so it's going to be 3 plus 1, we'll call that 4, 1 plus 5, 6, -2, -3, -5, and then we have 1 and 5, which is going to be 6 again. Nice. And this last one, I've left one that if you're learning this for the first time, you won't actually be able to, and that's going to be what happens if we multiply a by x. And yet another question, is that even possible? Okay, so that's going to lead us into our next topic actually, and that's going to be matrix multiplication. Now, before I teach you how to do matrix multiplication, I think it's very important that you understand the idea of a dot product, and that's something that you might not have seen before. So, a couple of facts about a dot product. It's going to be an operation between two different vectors of the same size. So just like addition or some of the other products or some of the other properties we've seen, dot product only makes sense if it's on two vectors of the same size. And dot products actually have a really cool like visual interpretation, and they can be described as like the alignment of two vectors, right? So I don't want to go super into the geometric part of it here, but I can just give you like a quick little picture. So let's say you have two vectors, and let's actually just say that they have a 90-degree angle in between them. Let me actually do them with different colors so it's not completely confusing. Okay, so we have two vectors, 90-degree angle, right? So in this case, we say that u dotted with v is going to be equal to 0. And this is by convention. So when two vectors have a dot product of 0, we can say that those two vectors are perpendicular or orthogonal, which are all saying the same thing. That's just saying that there's a right angle between them. And in contrast, if two vectors are kind of like they're facing in the same direction, that means like they're going to have the maximum like magnitude then. So these are just some cool properties of the dot product, but there's a nice geometric like interpretation. It's kind of like dot product essentially at its most like distilled way is saying how aligned are two vectors. Okay, so some notation stuff over here. This is how we write the dot product. You might have seen I just did that, where it's some vector and then just like this little dot with w. Okay, and the output is always going to be a scalar. So vector, right, is going to be something like this, and a scalar is just like a number, 2, 3, 5, whatever, anything like that. So finally, you're obviously interested, how do we actually compute this thing? So we're going to consider two vectors, v and w, both having length from 1 all the way up to n, right? And it's very important they have the same length. So v dot w is we're just taking the first two and multiplying them, and then adding the second two, and then so on and so forth. So it's v1 w1 plus v2 w2 plus v3 w3 dot 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 all the way up to vn wn. That's really all there is to it. Awesome. Let's try out two examples. So first we're going to do 1 times -2. So we're going to say -2 plus 2, which is going to be equal, oops, sorry about that, somehow switched over. which is going to be equal to 0, right? And if you remember from before, we can actually see that these two vectors are going to be orthogonal for that reason. Maybe if you want to just see like a quick picture how that ends up working out. So we have one vector is going to be 1 and then 2, so maybe something like that. And then we have -2, 1, which you could think is maybe something like that. So hope that makes sense enough why those two are perpendicular. Awesome. Let's take a look at some other ones. Let's see. So we have -1 times 4, -4, plus 3 times 2, 6, and then finally plus 12. So we're going to have -4 plus 6, 2 plus 12, which is going to be 14. And that's all. Dot products aren't too complicated, thankfully. So now that you understand dot products, let's get to the final topic of today's video, which is going to be matrix multiplication. And like I was saying before, with the scalar multiplication and our addition, matrix multiplication is also like kind of like a fundamental part of the whole thing. It's like in early levels of math, when you learn about addition and subtraction, they're kind of basic. So similarly, matrix multiplication forms a really, really important part of linear algebra. And a lot of really cool results come out of it that way. So now that hopefully it's motivated why we're learning about it, let's see how it's actually done. So I've actually left these empty on purpose because there's not really any reason for me to fill them. And what I'm saying, this important note that you should make for yourself, let's say that this first matrix has size A times B, and the second matrix has size C times D. This is only computable if B is equal to C, okay? That's a really important point. And the kind of neat thing, how it works out, is that the result will have size A times D. So you can kind of think in your head that this B maybe and the C are kind of like canceling out, and that's why like the A and the D are left over. So we have a much more concrete example here, because I know when everyone sees like all these letters, they get a little scared. So here we have a 2 by 2 matrix multiplied with a 2 by 1 vector, right? Since these 2's match, that kind of cancels, and then our output ends up being 2 by 1. So that's kind of nice how that works out. And then down over here, right, let's say we have two vectors that are being multiplied. So this one is 2 by 1, and this one's also 2 by 1. So these inner two numbers do not match, and as a result, this cannot be computed, okay? So hopefully, by looking at this, you might have realized, right, that if this times this can be computed, if you switch the order, it might not necessarily be the same. And that's a really important point that you should keep in mind. Okay, so I think we have some more examples over here. So this is kind of maybe the most confusing part of this video. Might not make a lot of sense right at first. So I'm going to say the ij entry in the output is the dot product of the ith row on the left. So ith row being, so this would be the first row, this would be the second row, right? With the jth column on the right. So this would be the first column, this would be the second column. So we're interested in columns here and rows over here, okay? So I've included a much more concrete like version of what you would be doing over here. And if you think about it, it kind of like works out really nicely how it is, because if you think of this element right over here in this matrix, it's going to be the first row in the first column, and you're doing the dot product of row 1 here and of row 1 here and column 1 here. So that you have kind of like, you're being told by the location what you're doing, right? So this is the first row, first column, and that's the dot product doing. This is the second row, and okay, so I actually made a typo there. So this is supposed to also be column 1. Oops. So that's pretty nice how that works out. So before we move on to the examples with the numbers, I could just show you. So in this case, right, this row 1 dot column 1 would be the dot product of AB with EG, which would be AE plus BG. Okay, let's take a look at an example. I know this is a little abstract when you're looking at it for the first time. I promise you, matrix multiplication is a little hard. I found it challenging, but you can definitely improve with practice. Okay, so we're going to be taking the first element, right? We want to find this first element over here. And actually, before we even jump into this, let's make sure that this is computable. So I'm going to shift this 1 down, and we'll see that the size of this first one is 2 by 2, This one is 2 by 1. These numbers match, and so our output should be 2 by 1, right? So we can actually already write this out as a 2 by 1. Okay, so this first entry, right, we can think this is going to be row 1 dotted with column 1, right? So we can just go ahead and do that. The first row dotted with the only column. So that's going to be 2 times 3. So we have 6. And then we're going to add -1 times -3, which is just positive 3. And then the bottom one is going to be row 2 times, or row 2 dotted with column 1, which is going to be 2 times 2. So I'll again show you. So the first one, we did the dot product of this and this. And the second one, now we're going to do the dot product of this and this. So that's going to be, we have 4 times 0 plus negative, or sorry, 4 plus 0 times -3, which is just 4 plus 0. Okay, and we can say that that whole thing is just equal to 9, 4. And that's kind of just all there is to it. Let's try a little bit of a more challenging case. This is going to be 2 matrices multiplied with each other. And before we actually do that, again, let's just check. So we have 2 by 2 over here, and this one's also 2 by 2. Those two numbers match, so we can expect 2 by 2 result. That's great. Okay, so let's start it off. So first thing we're going to do, right, row 1, column 1, we're going to do the dot product of this with this. So 1 times 0, 0, 3 times 2 is going to be 6. Now we're going to do the dot product of this, and that's going to be this entry down here, right? Because we're taking the second row and the first column. So second row, first column, right over there. So we have 0 times -2, 0 plus 5 times 2, which is going to be 10. And now we're going to be moving on to this entry over here, which we're going to get from doing the dot product of these two, which is 3 times 1 plus 3 times 1, which is going to be 6. And finally, our last entry is going to be the dot product of this here with that. So that's going to be 3 times -2, -6 plus 5, which is -1. And that's really all there is to matrix multiplication. So I have a couple last examples for you guys here. As always, compute the following if possible. Take a second maybe to do those on your own, and then let's jump right into it. So AB is going to be, we have 0, 3, 1, 4 multiplied with 1, 0, 5, -2. So the first one is going to be this dotted with this, which in this case, we're going to have zeros on both sides. So this dot product is actually going to be 0, right? We have some perpendicular vectors there. And then we can do this bottom entry over here, which is going to be this dotted with that. 1 times 1, just 1, plus 4 times 0 is just 0. So over here, we just have a 1. Then we're going to be doing the dot product. Let's do this with that. It's going to be 5 times 0, just 0, and then -6. And then what do we have? Finally, we're going to do the dot product of this over here with that, right? So we're doing row 2, column 2. And that's going to be 5 minus 8, -3. Yep. So these next ones, I won't talk through all my steps, but hopefully at this point, maybe you kind of see what's going on. Like I said before, this stuff is a little complicated, and it might take some time to get used to it. But I think by doing practice, it makes it a lot easier, that's for sure. Okay. So I just realized now, as I'm saying this, that I didn't actually show that these will multiply each other. Since we've done a handful of 2 by 2s now, hopefully you can see that the 2 by 2 multiplied with each other will always lead to another 2 by 2. So AB and BA are both defined, and they're both going to have 2 by 2 outputs, okay? So multiplying this out, what are we going to get? So we're going to have a 5 over here, -2 there. Then we have 3 plus 20, 23. And then finally we have a -8. And this is a really important point that we've found here, and that is AB is not equal to BA. Now that's not to say that AB will never equal to BA, but if we were to instead consider numbers, right, xy is equal to yx, that's kind of true, right, for all numbers. Their order doesn't matter. However, with matrices, the order in which you apply them does matter. And that means that AB is not necessarily equal to BA. That's a really important point. Okay, finally, let's take a look at AY. Let me make sure you can still see that. Oops. So 0, 3, 1, 4. Okay. So we have 2 by 2, 2 by 1. These match, we're good. Output is also going to be 2 by 1. So this first element looks like it's just going to be 0. And then the bottom one is just going to be -2, it looks like. Nice. Okay. Finally, we're going to be considering xy. So x is going to be 1, 3. And then y is -2, 0. And so this is 2 by 1, and so is this one. And so these two don't match, and this is going to be undefined. So we can never really multiply vectors. We can do dot products and stuff like that, but we can't multiply them in the traditional sense. So this video went on quite long, actually. If you stuck around all the way to the end, thank you very much. Hope this was helpful. I'll definitely be uploading more linear algebra videos in the future. If there's a topic maybe that you want me to make a video on, please reach out. I would be glad to do that. And thanks again. Have a good one, guys.